Okay, the second half of chapter 11 totally switches gears to looking at solids and their crystal structure. And we can classify solids in two ways. They can be crystalline solids, which are rigid and have a long range repeating order in their structure. So in crystalline solids, atoms, molecules, or ions occupy a specific position, and those positions are called lattice points. An amorphous solid does not possess an ordered arrangement overall. The unit cell is defined as the basic repeating unit in that crystal structure. So this represents a unit cell, and this represents the unit cells within a crystal. And again, this lattice point could be occupied by either an atom, a molecule, or an ion, depending upon what we are looking at, whether it's just a solid element, a molecular solid, or an ionic solid. So once again, one of those three will occupy the lattice point. So there's 7 types of unit cells. We're just going to look at 3 basic unit cells, but just this slide shows you the variation of unit cells that are possible. So there are 3 types of cubic cells that we're going to look at: simple cubic, body-centered cubic, and face-centered cubic. And we'll look at several of the characteristics of these. I've also posted a couple of animated videos that allow you to visualize the stacking pattern in these cubic cells. So please take a look at those. We're going to start with the simple cubic cell, sometimes abbreviated as SCC. You might see that. And essentially, here's the cubic cell, and we see 1, 2, 3, 4, 5, 6, 7, 8 lattice points, or 8 atoms, molecules, or ions present. And sorry, I started this before I realized I didn't turn my email notifications off. So by the next one, I'll have it turned off. Anyway, as you can see, now I lost my train of thought here. Well, I counted the 8 atoms, ions, or molecules. So these are all at the corner of this cubic cell, and this tries to represent or show you what portion of that atom, ion, or molecule is actually within the unit cell. This is the least efficient organization or structure of the 3 cubic cells we're going to look at. It's about 52% efficient. That means that 48%, or I'm sorry, 48% of this unit cell is empty space. Okay. So we can calculate how many atoms, ions, or molecules are within a unit cell, and we do so by multiplying the number of atoms, and I'm going to just refer to these as atoms now, although they could be molecules or ions as well. How many are in or occupy the lattice points, the portion of that atom that is actually within the unit cell, and this is 1/8 of that atom. So 8 times 1/8, gives us a total of 1 atom, ion, or molecule within the unit cell itself. Okay, so as packing efficiency increases, we're also going to see an increase in the number of atoms within that unit cell. Another way that we can look at the efficiency, or, well, yeah, it relates to efficiency, is if we take a particular atom and we count the number of other atoms that it's in contact with in that unit cell or in the crystal structure. So remember, these are going to be layered, and the layering pattern for a simple cubic cell is AAA. So every layer looks like this, and they stack right on top of one another. So in this, and this is called the coordination number, by the way, the number of atoms that are actually in contact with a particular atom. So we have 1, 2, 3, 4 that are actually touching that center atom. And then we have one above this in the structure or the crystal and one below it. So the coordination number is 6. We'll see coordination number increase with the increase in packing efficiency. Elements, or an element and a compound, an ionic compound, that utilize this simple cubic cell crystal structure are polonium, which is a radioactive element, and cesium chloride. And you should know the characteristics of these packing arrangements. The next one is called the body-centered cubic cell. And if we look at the center representation here, you see we have the 8 corner atoms that we had in the simple cubic cell, but we've added, or there's been added, an atom in the center of that body-centered cubic cell. So packing efficiency here increases to 68%, so 68% packing efficiency, which means that only 32% is empty space. The packing, and you'll see this in the little video, or the layering is AB, AB. So this is the first layer, and the second layer nestles in the opening between the atoms in that first layer, and then that first layer repeats itself again. So it's A, B, A, B. Okay, so that's the packing pattern. This is also called hexagonal close packed, or HCP, hexagonal close packed. Body-centered cubic can also be abbreviated as BCC. Okay. So, like the simple cubic cell, we can calculate the number of atoms actually within that cubic cell. So we still have the 8 corner atoms, which have 1/8 of that atom molecule in the unit cell, plus we've added that whole molecule in the center, or atom. So our number of atoms, molecules, or ions in this unit cell has increased to 2. So as I said, that's another indication of more efficient packing. We can also determine coordinations for each of the spheres in this structure. And I'm not going to walk through it because it gets a little more complex. But the coordination number Cn for the BCC is 8. So that's increased by 2. Anything else I was going to say here? Some examples. All group 1 metals utilize this crystal packing, and from the transition metals, cadmium, chromium, and iron. And that's not something you need to know, just giving you examples of the elements or molecules that might adopt these crystalline structures. The third unit cell that we're looking at is called the face-centered unit cell. And this is more complex, more efficient in packing. Again, there's a short video or animated video that allows you to visualize this packing. The packing is A, B, C, A, B, C. So there are 3 different layers. Packing efficiency is 74%. So that's an increase from 68%. The BCC. Let's see. So what does this look like? I'm going to flip to the, oh wait, well, I'm going to flip. Well, this, oh, I should go back. So there's a face-centered atom on each of the faces. So how many faces do we have? We have 1, 2, 3, 4, 5, 6. So each of these spheres on the face, or there are 6 of these spheres on the face of each of the sides of this unit cell, in addition to the 8 corner atoms. So this sphere is also going to be shared by, oh, this is a corner atom or a sphere. This is a face-centered, so that's shared by 2 unit cells. Oops. Okay, I thought I showed the layering, but I guess not. So let me add a little more to the face-centered information here. Should have done over there. The packing is called cubic close packed, or CCP. Again, cubic close packed or packing. Coordination number for a sphere in this unit cell is 12. And how many atoms are within the unit cell? Once again, we have those 8 corner atoms, of which 1/8 of those are in the unit cell. And then we have 6 face atoms, of which 1/2 of each of those is in the unit cell. So the number of atoms within a face-centered unit cell is 4. So simple cubic cell has 1, body-centered cubic cell has 2, and the face-centered cubic cell has increased to a number of 4 spheres, or atoms, molecules, ions, within that unit cell. Examples of elements or a compound that utilizes this packing: calcium, strontium, many of the transition metals, also some ionic compounds like lithium chloride. And yeah, I gave you the coordination number. 12 equals the coordination number. And remember, that is the number of other atoms or spheres that a particular sphere in the crystal is in contact with. Oh, sorry. Guess I wrote over that. All right, moving on then. There we can also classify crystals by their composition. And here we have ionic crystals. I will be making another video that will correspond to the cubic packing that we've just been looking at. That requires some calculations, so that will be a separate video because I can't do that with the PowerPoints. So anyway, ionic crystals. So in this type of crystal, then the lattice points are going to be occupied by ions, the cations and the anions. Here we have cesium chloride. Cesium is the cation in the middle, and then we have the chloride ions. And as you can see, this is a body-centered cubic cell. And here we have two other examples. No bonds here other than ionic bonds, which aren't chemical bonds, of course. They're held together by their attraction to one another, their plus minus charges. Typically, ionic crystals are hard and have high melting points. They are poor conductors of heat and electricity. However, they are water soluble. The, there we go. Covalent crystals then are, and sometimes called network covalent crystals. These are crystals that are formed by elements or atoms of a particular element. And we are looking at allotropes of carbon. I don't remember if we've discussed those before, but I thought we had. At any rate, in a covalent crystal, those lattice points are occupied by atoms, and thus they are held together by covalent bonds. Hard with high melting points. And again, you see graphite and diamond as examples here, two allotropes of carbon. Poor conductors of heat and electricity. Exceptions are diamonds and graphite. Okay. Whoops, here are some allotropes of carbon. So these are all different shapes, and I thought I showed you something similar. This is a buckyball, that's carbon 60. This is a nanotube, essentially. This is graphite. I'm sorry, this is coal. This is graphite. And we just saw diamonds on the other page. Let's see. So we have diamond, we have graphite, this is londolite, and I did already mention C60, the buckyball. This is C540, C70. So there are lots of allotropes of carbon. So next type of crystal is a molecular crystal. So as the name indicates, The lattice points in these crystals are going to be occupied by molecules. They're held together by intermolecular forces. So the molecule itself has covalent bonds, but the molecules are held together in the crystal by the intermolecular attractions between those molecules. Typically soft with low melting points, poor conductors of heat and electricity. Some examples here: ice, carbon dioxide, rock candy, which is made of sucrose. Next are metallic crystals. So lattice points are occupied by metal atoms. And we have, or I have mentioned to you, metallic bonding. So these are held together by metallic bonds. These range in physical properties. They can be soft to hard, have low to high melting points. It depends upon the identity of that metal. Generally good conductors of heat and electricity. And these crystals are described as a sea of electrons. So we have the nuclei of the iron, or the metal atoms, I should say, and the inner shell electrons, but then the outer shell electrons are kind of flowing around and belong to the crystal as a whole. Examples of metals examples. Most metals do this. Mercury, copper, iron, tungsten, so this is a table that just organizes some of the information that we just covered: ionic crystals, covalent, molecular, metallic, what forces hold those together, general properties. You don't need to know these. You should be able to relate the type of crystal with what's holding it together. And of course, you don't need to give me any examples of these. There should be one more slide here, and there is. I think it's only one. Yeah. So an amorphous solid, as we indicated on the first slide, does not have long-range repeating order in its arrangement. And here are two comparisons. This is crystalline quartz, which does have long-range repeating order, but this is non-crystalline quartz glass. And as you can see, it's quite irregular and none of the orderly structure that the crystalline quartz has. Coal is another example of an amorphous solid. So that's it for the crystals. Look for the example calculations video to come, and that should wrap up chapter 11, and we'll be moving on to gas laws in chapter 5. Sorry, I didn't realize that was on there.